Hi, my name is Matthew Anderson, and this is my lab report for Lab 3, the Black Hole Lab. The purpose of this lab was to analyze a model of a star's orbit to find the mass of the black hole and calculate the initial velocity of a ship in order to fly around the black hole without crashing into the planet or being sucked into the black hole. The physics fundamentals that this lab used were the momentum principle, F equals ma, Newton's second law, and Newton's universal law of gravitation, and a preview of the results, that is the mass and velocity that I found. So the fundamentals, of course, the momentum principle and all of its derivations, net force, and perpendicular parallel components of it. Perpendicular is mass volume squared over radius, changes direction, and the parallel net force component is change in momentum over change in time, and it changes the velocity. And the velocity and position update formulas we've used this whole time. We assume that force of gravity is net force. It's the only thing acting on it. And then we have universal gravitation and both versions of it. So it takes place in space. So all the forces acting on the star are the gravity of the black hole, and the only forces acting on the spaceship are the gravity of the black hole and planet. So net force is the force of gravity. Universal gravitation is non-constant in this case, so we assume average velocity as final velocity, and then we have the parallel and perpendicular components doing their parts. Perpendicular changes direction, parallel changes velocity. So on to some code. There's our givens. Set this to the net force, and then plugged in the formulas for the parallel and perpendicular components. Take all that and just plug it into the universal gravitation formula, and then set up the vectors visually. And this is just setting up the initial conditions and applying Newton's second law here. So the results of part 1, as you can see, it goes around without going into the black hole. There's my net force, the components of it, and the mass of the black hole, 7.88 times 10 to the 33 kilograms. So moving on to part 2, finding the initial velocity of the ship. The system is the ship, the surroundings are the planet and the black hole. Here you just set the initial conditions, plug in the mass from the last part, and then same constants as before. Then lots of lines of code for this part, but mostly just applying the formulas we've been working with this whole time. So here is finding R and R hat for gravitation. Here's plugging all of that into the gravitation formulas, and then this part is finding the distance to the ship and black hole between the two. And then applying Newton's second law one more time with the velocity update and position update to complete the iteration, and our print commands. So the results of part 2 here have the closest distance between them and the velocity, which I found just by plugging stuff in until it worked, basically. Possible errors I could have had are just general coding errors, which are likely because I am not good at coding. And what does it mean? So thinking about the rate of change in momentum and what net force means. So basically net force is the change in momentum over the change in time, or mass times acceleration. It shows all the forces on a system. Parallel component is parallel to the direction of the motion. It changes the velocity. The perpendicular component is perpendicular to the motion. It changes the direction. Changes in momentum are final minus initial divided by change in time. And momentum is mass times velocity. So it is easier to find the change in momentum than change in net force. And the what if, like I said, it's pretty difficult, so I wasn't ultimately able to figure it out. I know that to get it to work, the ship's velocity should be similar to the planet's velocity so they can orbit, but after tinkering with the code quite a bit, I could not get it to work. I just kept crashing into the whole black hole over and over again. But that is pretty much it for my lab.